Okay, so for the last part of the tutorial, we're happy to have Simon Mauras, who's going to tell from India, who's going to tell us about private interdependent valuations. Take it away, Simon.
Hi, so thank you for joining us for this last part of our tutorial on interdependent valuations. So on the first part, Divya presented standard results in auction design for a single item auction with the interdependent values and how to achieve a full approximation in that setting. And in the second part, Rebecca explained how to relax one of the assumptions, which was the fact that buyers were offline. In this third part, I'm going to talk about another relaxation, which is what about the case where valuation functions themselves are private. So it's back to the offline setting, but the generalization of the first part is the valuation functions. So that we are all on the same page, let's start directly with this the setting. So we have an input, and as input we have n buyers, and each buyer will have both a private signal, say SI, and also a private valuation function that aggregates all signals into some value. And so the goal of our problem is to find some allocation rule, x1 through xn, which is the probability of each person getting the item, maximizing what is called the social welfare. It's the expected value of the person who gets the item. Once again, we care about truthfulness, so we want the buyers to report truthfully, so we will see that a bit later. And our goal is to find some approximation guarantees on the approximation ratio, which is an upper bound on the ratio of the optimal value divided by the social welfare achieved by our algorithm. Okay, so now the question is, why is it harder to do this when valuation functions are private? Let me start with a small example. So this example is what happens if one agent holds all of the information. So think of this example as every buyer I has a value equal to I times S1. So S1 is the only important information. It could be 0, it could be 1. So in this case, this is very easy when the valuation functions are public. So clearly because agent 1 has the worst value no matter what, and agent n has the best value no matter what. So you can just even ignore the signal and select the nth buyer, and you will always be optimal. So this is trivial in the public valuation setting. But the problem comes when you have private values, because agent 1 may lie in a very complicated way, which is report their own signal to be 0, which causes everyone to have a 0 value, but then also lie about the valuation function so that they're the obvious candidate to get the item. And so this is harder because now the mechanism facing this instance is wondering what happened. Is it that agent 1 lied, in which case agent n should still be selected? Or is it that agent 1 didn't lie because that was the instance all along, and in which case 1 should be selected? So this is like an extra challenge the mechanism has to face. And in this situation, okay, maybe we can select either 1 or n at random, which would give us a 2 approximation. But in fact, you can generalize this example to something much harder. So look at this instance where every buyer's value is going to be the product of all of the signals. And all the signals in this instance is going to be 1. So once again, this is a very easy example with public valuations. Like we have identical valuations. So technically, no matter what we do, we achieve optimal welfare. And also it happens to be single crossing. So remember, Divya said then with single crossing valuations, we have optimal welfare if we have public values. But in a private case, this is harder, right? Because in this fully symmetric instance, there must exist one agent I who gets the item with probably at most 1 over n in the original instance. But now this person I, say I equals 1, they could lie and misreport a signal and say 0. In that case, what happens? So every other agent will have a value of 0 because we have this product here. But to be sure this person gets the item, they misreport their valuation function to be positive, although the signal is 0. And so you can check this is still single crossing. But here, here the only person with the positive value is going to be agent 1. So the algorithm once again is facing this dilemma where they don't know if it was I lying or I having this value all along. So if I lied, they shouldn't receive more than what they received in the first place, because that would have been a successful manipulation from the agent 1. But at the same time, if agent I was not lying and it was their true value, then we should give the item to that person. And in which case, the ratio between what opt achieves, which is 0.5, here 0.5, the value of agent 1, and what the social welfare of our algorithm constrained to be truthful achieves, being 1/n, we cannot have better than the n/2 approximation. So our beautiful results in the public setting, when we have single crossing valuation functions achieving optimal welfare, this is no longer true in the realm where we allow agents to misreport their valuation functions. Right, so this is very bad, but what can we do? How can we even achieve truthfulness in this setting? So remember what our notion of truthfulness was, this notion of ex post incentive compatibility. We want truth telling to be a Nash equilibrium. So we're going to consider this game where agent will first report the signal. Then the mechanism might query agent's valuation functions using the signals. And we want that in this game, truth telling must be a Nash equilibrium. This would be our definition of what truthfulness, incentive compatibility means. And so this is a strong requirement, but we can come up with some sufficient condition for this to hold. So let me explain quickly. So xi, remember, is the probability that agent I received the item. And we can make sure that it only depends on S minus I, the other agent's signals, and V minus I, the other agent's value, and also maybe their own value evaluated on all signals. And so if it happens that this function is non-decreasing in VI of S, we will be able to use the same trick as before, which is charging Meyerson's prices to make sure that agent tell the truth in equilibrium. So this condition is also almost necessary. This is a characterization by this paper of 2022. And every paper that worked on private valuation functions is considering this notion, this sufficient condition to come up with mechanisms. Okay, so how do mechanisms work? Let me tell you which framework, which construction has been used in the past in the literature. So the main idea is to use a sub-mechanism Y. So think of this sub-mechanism as a mechanism to allocate in the private independent value setting. So no signals, just private values. Let's call it weights. So each agent is going to be selected with a probability that depends on their weights. And we want the probabilities to be non-decreasing in their own weight, because that's going to be useful for truthfulness. Also, later we will fix some constancy to be chosen in the analysis. It's not important for now. And so what our meta mechanism is going to do, it's going to choose the probability of agent I to be running this sub-mechanism Y using an instance where you have agent I having their true value, but everyone else having low estimates or proxy values, which only depends on other people's report and do not depend on their own, on I's report. So this is very important. This quantities only depend on S minus I and V minus I. And this by monotonicity is going to be a monotone function of VI of S. So this meta mechanism satisfies the sufficient condition that we set on the previous slide. This is great. But now we need to show that this is actually a good mechanism. And so as you may have noticed, there is a small 1/c constant here. And this is really the main challenge of this approach, because our goal is going to be to set C such that the sum of probability will be at most 1. So we don't want to over allocate the item. We don't want to promise it to more people than we have items, right? And so because we're running this algorithm Y multiple times with other people having scaled down values, maybe the probabilities Xi's are going to be too high. And so maybe we will have this problem of promising the item to too many people. And that's where this parameter C comes into play. And so you can think of the y1 through yn to be some kind of soft argmax function that will try to select the max, but try also to be smooth so that it's robust to small changes in people's value. And you can think of C as a bound on how much yi, so the probability, will increase on average when you decrease j's weights from their true value to their low estimate proxy value. So this is a construction that satisfies the sufficient condition. And if we choose C in the correct way, will be feasible. And if also the mechanism itself is well designed, we might be able to prove some approximation guarantees. Okay, so let me directly jump to the known results. So all of these three results are following this framework of a meta mechanism using some sub mechanism. So the first paper introducing this problem of private interdependent values was introduced in 2022. And so they gave a log square n approximation, n being the number of agents. And in their construction, yi was proportional to the inverse of wi's rank in the set of all weights. So this is a smart construction, and their proof was using some argument from extremal graph theory, like the coloring number of a directed graph with a bounded degree. We're not going to go too much into these details. A later work in 2023 come up with the 5.55 approximation, where y can be seen as a smooth variant of random serial dictatorship, which is a mechanism to allocate items that uses some random order and also permutations. The proof of this relies on some math, just carefully tracking the probabilities, how much that increase. And very recently at EC this year, we have this improved 5 approximation where instead of using random serial dictatorship, you use a smooth variant of probabilistic serial, which is another mechanism where the advantage here is that we can even describe it as a solution of a linear program and bound all the probabilities with the dual of this linear program. So I'm not going to talk too much either about this improved 5 approximation, and I'm going to focus on this. I'm going to explain next what is the intuition for this first constant approximation. And as Alan said in the chat, this 5, I lied, it's not exactly a 5, it's a 4.99, but yes. So 5 is definitely not the exact constant. There is a lot of work. If we can even, maybe it's possible to improve this constant. Okay, so I said that we're going to use this mechanism, and I also said that y can be understood as a soft max. But one question is, what happens if we use the hard max sub-mechanism? So hard max is just take someone if and only if they're the maximum weight, right? And maybe there is many of them, so we'll just allocate to one maximum at random. That's what this expression is doing. So in this hard max sub-mechanism, if we use it, we're going to say that an agent I is going to be a candidate if their true value exceeds other people's low estimates for every other agent J. And so this is a sufficient and necessary condition to get a positive probability in this meta mechanism, because look here, we're selecting the hard max according to the true value and low estimates of others. So someone is going to receive a positive probability if and only if they're candidates. But this can be terrible, because what can happen? So look at this instance where you have every person's value is just the sum of signals, right? So the people's true values are all equal, But now if you compute the low estimates, everyone is going to be able to lower a bit other people's value by taking a zero signal. So all agents are going to be candidates at the same time. Very bad. Very bad. Why? Because if you want this to be feasible, you want the sum of xi's to be at most 1. And so you really need to set this constant c to be equal to n, which in terms, for another instance, we'll just say that you cannot allocate anyone with a probability more than 1 over n, which gives you a n approximation. Not great. So we know how to do an approximation, but that's not good. But this mechanism, this hard max sub-mechanism, is still teaching us something, because we can give improved guarantees in some specific setting. And so now I'm going to focus on this, and it's going to be the proof of this part of the tutorial. Assume now that every person's value only depends on D signals. So this is good. Why? Okay, first, I'm going to call I star the highest value so far, the highest value considering all of the signals. So obviously this person is going to be a candidate, because if they're the best with all the signals, they're also the best compared to other people's low estimates. So I star is a candidate. They will have a positive probability. But now for another agent I to be a candidate, it must be the case that VI star depends on SI, otherwise they won't be able to beat that person. So because VI star is only depending on D signals, there is at most D plus 1 candidates. The one being I star, and the other D being the D people whose signal influence VI star's value, right? So good. Now what we can do is just set C to be equal to D plus 1. And by construction, the sum of xi is going to be at most 1. So we obtain a D plus 1 approximation mechanism. Great. Okay, but this is good, but this condition here is very strong. Every person, depending on trusting only D other people to evaluate their signals, their values, is a very strong assumption. So we would really like to get rid of it, obviously. And so remember, in Divya's talk, she introduced the class of submodular over signals valuation functions. So here I try to reproduce the picture. So the definition of SOS, or submodular over signals, is just technically means that the influence of one signal is lower when the other signals are higher. So here this difference is lower than that difference because orange signals are higher. Okay. So this is a property used in the public valuation setting, but we can also make use of it in the private valuation setting by saying, well, this class of SOS valuation is going to satisfy a property that is called self-boundingness. Self-bounding meaning that if you compute the sum of all agents J of how much the value of I decreases by replacing Sj by 0J, overall, this entire sum cannot be bigger than the value of I itself. And this is a property known to people who work on submodular valuation functions. And this is going to be the key lemma, the key property that we're going to use here. Okay, so in particular, one very good property that we have from this is look at this right-hand side term here. It must be the case that there is always at most one J such that the low estimate VI0J is much smaller than VI, much smaller being a factor 2 smaller. Because if you had two of them, then this sum would be too big and this would not work. So it would be a contradiction. So using SOS, so from now on, we're going to assume valuation function are submodular. We're going to use the property that this implies self-boundingness, and we're going to use the property that at most, for each person, at most one other agent can decrease significantly their value by a factor 2 or more. Okay, so how can we use this? let's try to see how we can do. So remember, we said something about people's valuation function only depending on a constant number of like deep other people. So our hope here is take the value of people, wj, and round everything down to the nearest power of 2. And so the hope is, now that I've rounded the values to fixed like levels of 2, maybe because of this property of self-boundingness, not too many people will be able to make me drop from one power of 2 to the next one. And so this is the hope. And we're going to say that an agent is a candidate if their rounded down value is bigger or equal to every other people rounded down low estimates. So that's going to be the construction. So that was our first try, but this unfortunately doesn't work, right? And let me show you why it doesn't. Imagine that everyone has a value equal to 2.001, but if you compute the low estimates, every low estimate is going to be 1.999. This is very close, like the two are very close, so it doesn't contradict self-boundingness. If you compute the sum of these differences, it's definitely still going to be low. But here we're really unlucky because we are dropping from 2 to 1 for every possible instance of this Y mechanism. So really, we have too many candidates. We would still have to put C as a huge count, even equal to N, and we cannot guarantee any constant approximation. Right, so how do we solve this problem? So here we turn to randomization. So that's the final trick to get a constant approximation. So we've seen that the main problem was this threshold of 2 being exactly in the wrong place, like exactly between the values and low estimates. So what if now we decide to round down, not to a power of 2, but some like randomly shifted power of 2. So I'm going to call FR this randomly rounding down function. And we're going to take the expected value over the random shifts of the powers of 2. Okay, and now we're in happy territory because we can show that there is at most 4 candidates in expectation if we use the randomness over R. So I'm not going to give you the proof. This is too technical for a tutorial. If you want to see it, you can have a look at this paper from last year. And the good thing is, using this bound of 4, we will be able to set the constant C equal to 4, and we will obtain something which is an 8 ln of 2 approximation because of this inequality that I wrote multiplied by the factor 4 that we get from the scaling down in the mechanism to ensure feasibility. Okay, so overall, that's how you can achieve a constant approximation, even if you don't know the valuation functions. And you're using here some tricks with randomization and the framework that we used, which was using the sufficient condition for truthfulness. But there is a lot of other things that we can do. So let me quickly go over some extensions that we can have. So in every part of this tutorial, we have been assuming that valuation functions are monotone over the signal. So signal was just some quantitative information of how good the item is. And so you had a valuation function that was aggregating all of that. But signals could be more complicated. For example, you can say that S1, the signal of agent 1, is the color of the cat that you want to buy. Or maybe a buyer 2 knows the shape of the cat. Okay, that's a terrible example, but so in these settings where signals capture more than just quantities, we cannot really talk about like what monotonicity means, because these signal spaces are not even ordered, right? So we cannot define these low estimates, and submodularity itself is not really well defined. But all of this is okay because I'm not going to give too much details, but you can replace the low estimates by some other definition. And the self-boundingness property that we've been using so far is still well defined even without ordered signal spaces. So all good. So we can extend all of what we said previously to non-ordered signal spaces and non-monotone valuation functions. Great. Okay, second extension. Maybe you're happy with submodular of a signal's valuation function, but your valuation function is not quite exactly submodular of a signal. Maybe it's like slightly more complex than that. And maybe it's non-monotone, or maybe it's a bit more general than that. And so you want to have a mechanism that would work for every valuation function, not only the SOS ones. And so in this second extension, you can actually try to relax the notion of self-boundingness by introducing some multiplicative factor D, which would give you a hierarchy of valuation functions, which eventually captures all functions. So if you look at this sum, it's very easy. If you take D equals N, this inequality is always going to be satisfied, right? So this hierarchy of valuation functions captures all the function, and depending on where your function lands in the hierarchy, that will tell you how hard this instance is going to be. And so we can show that with the previous construction, there is at most a linear number of candidates, linear in D. So in particular, when D is small, you have a constant. When D is N, you have an order N approximation, which is the worst you can get, even with like this randomly allocating an item to one person. And that implies that we have a truthful D approximation in that setting. Okay, we can also make this mechanism oblivious to D, but this is another story. I'm not going to tell you too much about this. And I'm going to wrap up with this last extension by a small summary of what I presented. So we considered this generalization of the auctions with interdependent values by making the valuation functions also private. So that makes the problem more complicated, but we can still achieve a constant approximation, assuming some property like submodularity over signals. And we've seen that this result extends to, we have two interesting extensions. Like you can also deal with non-monotone valuation functions, which, by the way, we didn't know how to deal with that in the public setting before. With this random sampling mechanism was also relying on monotonicity and ordered signal spaces. So this is very nice that then we can get rid of this assumption and get a constant. And also we can have an approximation ratio that depends on how complicated the valuation functions are, which is this hierarchy of valuation function and the approximation ratio that depends on that. Okay, other extensions. Most of what I said before we can make it work with having to allocate multiple identical items, and more generally in settings that are known as a single parameter. Every person is described by exactly one value. So there is some work in matroid selection. If you want to select a set which is independent and trying to maximize the sum of values of people in the set. But there is a lot of open problems. In particular, if you go beyond this single parameter assumption, right? So what are the open problems for this part of the tutorial? Can we get any upper or lower bound, improved upper or lower bound? So the best known lower bound is 2. It's the one from the public valuation setting. And the best upper bound is going to be 5 with submodular over signals valuation functions. So can we close this gap between 2 and 5? And so this would require coming up with a smarter Y. So I'm sure there is a lot of you who will be able to come up with smarter Ys than what we did. And can we allocate multiple non-identical items? This is another like multi-dimensional open problem. And finally, interdependence is a very interesting concept that makes mechanism design a bit harder when you already know how to solve it with private independent values. And there have been a lot of work in mechanism design and optimization in plenty of different settings where people have managed to tackle other harder problems. And maybe for these problems where the answer is known with independent values, adding interdependence could be an interesting direction. So thank you for listening, and if you have questions, we'll be happy to answer.